Hey everybody, permutations and combinations, that's what we're doing today, and I'm going to try and make this as quick as possible. If you see up here, we've got 19 slides to go through, and not wanting to take this forever in terms of making a video, you're on your own, just like the last one that was really long. I'm going to challenge you. It's probably going to take you half an hour to go through this, even if the video is only 15 minutes long. I need you to stop, check out the examples, take your notes, make good effort to make sure you understand this. I'm going to leave some time for you to pause, let you know when those times come, time for you to think over some examples. But again, I need you to take the time on this because I'm not going to. I'll explain everything I have to, but it's up to you to stop, slow down, and make sure you understand, okay? This one is huge. It's something brand new probably for most of you, and it will come back, I promise. You'll be doing this next year in Algebra 2, and it continues to come up for the rest of your life. So, permutations and combinations. All right, our vocab, fundamental counting principle, factorials, and then obviously permutations and combinations. And you can find this in the text section 13-3. So let's get into it. Let's start with something that we have done before. You probably remember this from middle school, this kind of problem. So you have jeans and dress pants, two selections, two possibilities for what you're wearing for pants in a day. As for shirts, you can choose a t-shirt, a hoodie, or a dress shirt. And how many combinations are possible? Well, if you're anything like the kids I taught in middle school, what you did was you took your two possibilities for pants, jeans and dress pants, and you made a tree, right? Where for each of these possibilities, you branched them off into the shirt selections as well, right? T-shirts, hoodies, dress shirt, t-shirt, hoodie, dress shirts, one for jeans, one's for dress pants, and you would have found out that you had a total of 6 possible outfits. All right, we're going to formalize this now a little bit and saying that whenever we have an event M, and it could happen in M different ways, and a second event, we'll call it N, which can happen in N ways, the event M followed by event N can occur in M times N. So we had 2 pants, 3 shirts. We ended up with 6 possibilities, 2 times 3. All right? So if you go to lunch, 5 choices of sandwiches, 6 choices of chips, 3 choices of drinks, what you're going to find out using the fundamental counting principle is that you got 5 times 6 times 3, or 90 different possibilities. All right? So again, you probably remember making trees. I don't know if this was ever spelled out to you before, but this is called the fundamental counting principle. All right. So let's make it a little harder now. All right. Again, I'm assuming you guys did that sort of thing in middle school, but now we're going to talk about what is a permutation. And I'll let you pause here and read the definition, okay? It's an order of arrangement in which the items of items in which the order of the items is important. Now we can use the fundamental counting principle up to a point to find a total number of permutations, okay? So if you wanted to line up 4 friends, well, any of the 4 could be first, then any of the remaining 3 could be second, the remaining 2, any of them could be third, and the last one, well, there's only 1 left there. So we can use the fundamental counting principle, 4, 3, 2, 1, to get 24 possible permutations, okay? So now, a little bit of background. Let's talk about what a factorial is. So over here we said we had 4 friends. We ended up with 4 times 3 times 2 times 1. That's called a factorial. 4 times 3 times 2 times 1 equals 24. And we say that's 4 factorial, and we write it using this notation right here, okay? 4 factorial means 4 times 3 times 2 times 1. All right? So 6 factorial looks like that, and the final result is 720. And our definition here tells us that n factorial is n times n minus 1, all the way down to 1. Okay? By the way, by definition, 0 factorial equals 1. Okay? So take that in. That's a factorial. We're going to be using those a lot this section, okay? Here goes. So, say you wanted to arrange 12 books on a shelf. how many different ways can you line them up? Now the order matters. We got to put them 1, 2, 3, 4, 5 up through 12 on the shelf. Okay, we can't just. It's not like we're lumping them all together in one bag, which we'll talk about later. Okay, so the order matters when we do this problem. Therefore, it's a permutation problem, and we can use the fundamental counting principle. So give you a second here to pause it if you want to work it out on your own. Okay, and if you don't, here's what we got. We got 12 factorial, 12 times 11 times 10, 987, all the way on down. We end up with, what is that, 479 billion possible permutations on the ways we can arrange those 12 books on our shelf. Okay? Okay. Now, here's where it gets a little tricky. If we have 12 books, but we're only going to put 4 of them on the shelf, how many possible arrangements can we make up using 4 of these 12? Okay, well, we could have 12 possibilities for the first spot, 11 for the second, 10 for the third, and 9 possibilities for the fourth. But that's where we have to stop now. All right, so our total number of possible permutations is just 12 times 11 times 10 times 9, or 11,880 permutations, okay? Since we're not going all the way down to 0, we're only choosing 4 books. We're going to stop right there, 12, 11, 10, 9. Okay. So the number of total possible permutations is 11,880. Now I want you to see what happens here. It's like we did the 12 factorial, but we didn't use that 8 factorial part of it, okay? So we kind of just stopped without using that, okay? So it's like, in effect, what we did was we took 12 factorial and divided it out by 8 factorial, because look what happens here. We're going to cancel 8, 7, 6, okay? So it's like a division problem where we're canceling out all of these factors to leave us only with that part we were talking about, okay? So does that make sense? We're using the 12 factorial, but we're not using the 8 factorial part of it. Okay, so remember the original problem. We were taking 12 things, 4 at a time, and look what happened. Look what we ended up doing. We put 12 factorial on the top of our fraction and 8 factorial on the bottom. Well, 8 factorial happens to be our 12 minus our 4. Okay? And this gives us a nice formula for finding the number of permutations for any set of n items, the total number, 12, but we're only arranging them r at a time. In this case, it was 12 items, 4 at a time. Check it out. Permutation, we can use this formula. And we write it this way with the n first, the total number, then the p means permutations, and the r means how many we're arranging it at a time. And we use, just like we did before, 12 factorial over 12 minus 4 factorial to give us our total of 11,880. So does everybody see? There's our formula for the number of permutations. Okay, total number divided by n minus r, factorials on both of them. Good, good. All right, digest for a second, pause, and I'm moving on. So, example, if we wanted to choose class president, vice president, secretary, 10 people in class, okay, now we make it totally random, we draw names out of a hat. Well, the number of possible permutations would be 10p3, or 10 factorial, over 10 minus 3 factorial, 10 factorial over 7 factorial. Once again, we're going to cancel out everything from here on over, and it leaves us 10 times 9 times 8, or 720 possibilities for our class officers. All right, next thing we got to know. A combination now is an arrangement of items, but the order's not important. This is like we were throwing 4 of our books into a bag, and it doesn't matter what order we throw them in there. The book says if we're making a fruit salad and we can choose any 3 possible fruits, you know, it doesn't matter what order you put them into the salad, you're just lumping them all together, okay? So maybe we're picking 3 students out of 10 to do a problem on the board. They're working together. It doesn't matter what order what order we select them, okay? So this is called a combination as opposed to a permutation, okay? So a combination, the order is not important. The formula we have for combinations, well, it's the same as the permutation one, but we throw in an extra r factorial on the bottom. Okay, so the number of combinations of n items in a set arranged r at a time looks like this. And we use a C this time for combinations, and we added that R on the bottom of our fraction, okay? So I'll give you an example here. We're choosing 3 students to work at the board, 10 students in the class. We use the combinations formula, 10 factorial over 3 factorial times 10 minus 3 factorial. Ends up looking like this. We still cancel out the 7, 6, 5, 4, 3, 2, 1, but we end up with the 10 times 9 times 8 over 3 times 2 times 1 for a total of 120 possible combinations. Okay, so you notice our combinations are always going to be smaller than our number of permutations because we're dividing by that extra r factorial. So when we were choosing class officers, we used the 10p3 formula, going back here, and we found 720 possible permutations when the order mattered. When the order didn't matter, we ended up with 120. Okay, using the combinations formula. All right, getting close now. We're throwing 4 of our 12 books in a bag for the library. We're using the combination formula now. Here's our extra r factorial, and we end up, instead of our 11,000 that we had before, we end up with 495. Okay, now it gets a little tricky when to decide when to use permutations and when to use combinations. Okay, so we're trying to decide on 3 electives to take over the next 3 semesters. You have 5 choices to pick from. How many possible ways can you arrange this schedule? Well, if you want to try and work it off on your own, now would be a good time to pause it before I move the question marks. Okay, hope I gave you time. Here we go, here's your answer. In this case, the order matters since you can only take 1 elective each semester. So you use the permutation formula, 5 factorial over 5 minus 3 factorial, and it gives us 60 possible ways to schedule these 3 classes. Next example. I evidently lost my question here. Let me see what I got. There we go. A jury of 12 people is chosen from a pool of 35 potential jurors. How many different juries can be chosen? Okay. Once again, pause if you want to do it on your own. But here we realize 12 people are chosen. Order doesn't matter. We're lumping them all into 1 jury. We'll use the combination formula. So 35 factorial on top, 12 factorial times 35 minus 12 on the bottom. We get 834 some million possible juries that we can make out of a combination of that sort. Okay. Finally, we use these things to figure out probabilities. We got pool balls that were taken from a set numbered 1 to 15. What's the probability that we choose the balls numbered 5, 7, and 9? Okay. Well, we're going to use our probability formula and take the possible ways to choose 5, 7, and 9, and then divide that by the total number of ways we could choose 3 balls. So, the number of possible ways for 5, 7, 9 over the possible ways to choose any 3. Okay, we'll use the fundamental counting principle to figure out the top, okay? 5, 7, and 9, we're just going to use 3 times 2 times 1. There are 6 ways to do that. Now, for this, the order doesn't matter. For the bottom, the number of possibilities for the bottom of the fraction, we're going to use that combination formula, right? Okay, so we'll end up doing the combination formula right here. 15 over 3 factorial times 15 minus 3 factorial. Combination formula, get rid of that. Bad news, mistake. Grab this tool. Okay, go right over here. Combination formula for the bottom of the fraction. So on the top, we ended up with 6 from the fundamental counting principle. On the bottom, we ended up with 455 from the combinations formula. So our probability of choosing 5, 7, and 9 out of 15 random balls is 6 out of 455. And I hope I made that quick enough. Again, up to you to go back if you need anything else. We'll practice on this a little bit later. In fact, here's your homework assignment. We'll make it due Thursday, and I will see you all soon.